Okay, so in this presentation, I'm going to outline how we can use a method called symmetric key encryption. So symmetric key encryption is all about using the same key to encrypt as we used to decrypt. Later on, we'll look to see how we can pass that key between Bob and Alice. But for just now, we'll look at a very efficient method of protecting our data, and that's with symmetric key. Okay, so we'll look at some of the basics around that, and then go on to the difference between a block cipher and a stream cipher, and then touch base with some of the methods that we might use for symmetric key. And then what happens if we end up with the same cipher each time that we encrypt? It's possible for Eve to copy and paste that and do a playback attack. So we'll have a look at what's called salting to make sure that our ciphers always change. And then the various modes that we have along the way, and we'll see how they are used. Touch base on 3DES. It's kind of older cipher, but still in use in some places. And then on to an alternative to the AES standard, and that's with ChaCha20. Finally, we'll look at key entropy, and that's looking at the strength of the key, and then on to how we can use symmetric key encryption within public cloud infrastructure. Okay, so here's the basic diagram that we might show when Bob and Alice are communicating with each other. So we need to make sure that the data is private, it has some integrity and so on. So we build then different methods to make sure that we have integrity. But for the core privacy, we often use symmetric key encryption to encrypt data and also when it's been transmitted over a network, such as through an encryption tunnel. Symmetric key encryption is a fast method compared to asymmetric encryption, public key encryption. So we typically use it when we have quite a lot of data. With public key encryption, we often use that when we've got a little bit of data. And I'll explain later on how we use public key encryption. But if we assume that on either side there is the same key, then one key will lock the data or create the ciphertext, and the same key will be able to unencrypt it or decipher it. We obviously need to get the key from Bob to Alice in some way so that Eve doesn't discover it, and as we'll find out in a later unit, we'll use a key exchange method to do that. Okay, so here's a quick question for a 128-bit key, and let's say we can try 10 billion keys per second. So the way that it can work is that we can keep trying a key and we create an exception on the ciphertext. So we know it's not the right key because we create the exception. If the exception doesn't happen, there's a chance that the key is correct, and then we could try to decrypt and see if the plain text makes sense. Okay, so for this we have 2 to the power of 128 different keys, and that's a lot of keys. But let's say we tried 10 billion, that's 10,000 million keys per second. Through brute force, how long do you think it would take? 10 days, 100 days, a year, 10 years, 100 years? What would your guess be? Sounds like maybe a year or 10 days? Well, no. For that, it would take 529 million years to be able to find the right key. Would obviously take half that time on average, but that's still an awful long time. Okay, so brute force with a random key is unbelievably secure for 128-bit encryption. In fact, we would need all the energy to boil every ocean on the planet over 16,000 times to be able to find the encryption key. So that's one measure that we can have when we look at the security of our encryption keys. We can look at the amount of energy that we might need to be able to crack a certain key. So we see here, up to about here, it would only require the energy to heat a swimming pool. Not too bad. If we think the break point is around here between being able to boil the rain and to be able to boil a swimming pool, there's a big difference between those two. Obviously, as we move up here, no agency on the planet could actually support the cost of boiling a lake, especially not a sea and so on. So the break point happens somewhere around here, and we can define that roughly as 72 bits. So 72 bits of a symmetric key is probably the limits that we have for our encryption. Anything more would be too costly for a random key. When it comes to hashing, we can see here, and we'll find out later, that 128-bit hash is quite easy to crack. So we need larger sizes, and this region here is now being called into question because that's SHA-1. And if possible, we should be moving up towards 256-bit hashes here. And when it comes to RSA, or public key, we can see that we need probably more than 1,000 bits of RSA modulus there. If possible, we're moving up about here. So 2048 bits is a very typical size of an RSA key, and 4096 is probably preferred there. So if possible, we want to be moving away from the threshold here to make sure that it becomes more and more difficult for our adversaries to be able to crack. Obviously, if we're the adversary, then we probably want to find weaknesses within the encryption process to be able to crack. But this is a baseline cost that we would see. Okay, so you can see here the different levels of the keys. We will concentrate on symmetric key encryption here, and as long as we're above about 72 bits and moving towards 128 bits here, then we will be okay. Okay, so let's look at some of the basics around symmetric key encryption and each of the areas that are relevant. Okay, so we have Bob and Alice. We need to make sure that there is privacy, there is identity. That's Bob can identify himself to Alice and vice versa, and then there is some integrity in there. So we often use symmetric key encryption for that privacy, identity, public key, and integrity can come with both public key and asymmetric key and symmetric key. Okay, so basically what we do is that we have a standard encryption algorithm that both Bob and Alice know about, and even Eve knows all about the encryption algorithm. It's well published, the source code is available, everything is open about it. But we have a key, a special key that only Bob and Alice will know. The problem that we have is obviously if Eve discovers the key, it's very difficult for Bob and Alice to know that she's actually discovered it. But if we have enough of these keys, then it's going to be extremely difficult for Eve to search through all the keys. She might be lucky and get it first time, or she might have to go to the end, but on average she'll be going through half of the key space to be able to find that. And the greater the key space, the more secure the key will actually be. Sometimes in encryption what we have is what's called key rotation, so that we use a key only for a certain amount of time. Just in case Eve manages to discover that key, we rotate the key so that we have a new key next time, and both Bob and Alice can actually do the rotation themselves. Okay, so here was the classifications that we have. RC2, RC4, DES, 3DES, AES are symmetric key methods. Same key is used on either side. We have asymmetric methods where we have a public key and a private key. The public key can encrypt and the private key can decrypt. In the same way round. RSA is a very typical method for this, and elliptic curve methods. For a one-way hash, we can only go one way mathematically, and we can't do the reverse back again. And the typical methods are MD5, 128-bit hash, SHA-1, which is a 160-bit hash, and SHA-256, or SHA-2, as we often call it. It gives a 256-bit hash. And then the final one is not a way that we can actually encrypt at all. It's purely just encoding, and then we often use base64, hex, octal, Unicode, and so on. Okay, so the number of keys that we have relates to the number of bits. 2 to the power of the number of bits gives us the number of keys. So we can see here that 2 to the power 20 bits gives us 1,000,000 keys. And then we can go up there. So there's a lot of keys in there, but as we've seen, it may be possible for 72-bit keys to be cracked. So every time we add a bit, we double the strength of the key. So when you go from 72 to 128, that's double, 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 and so on. And it increases the security vastly. Okay, so let's take an example. We'll take a relatively small key size of 64 bits. There are these number of keys. So let's see how long it will take us to crack that with brute force. Okay, so I reckon if we use a nanosecond clock and check each key 1 nanosecond, that's 1 billion keys a second, then I estimate that's about 9 billion seconds, or 285 years to be able to crack that. Okay, but one thing we know about Moore's law is that computing power can actually computing power increases each year. So let's say that we double the computing power, then after 1 year, then we take half the time. And it doesn't take too long to actually find out that something that took us years to be able to crack can be cracked in days or even minutes. If you think that DES, 56-bit DES in 1975 was the standard, and that was many years ago. The other thing that we can do is that we can parallelize the setup. So rather than having one processor, we can have two cores, or we can have 4, 16, 32, and so on. And this is just like a GPU set up with little cores that are very good at mathematical operations, such as hashing and symmetric key. So it's possible for each of these cores to be given a split of the key set. So we would just split by a 16th, and then each of the cores would actually try out their set of keys, and then eventually one computer might say that they've actually found the key here, and we can actually stop the process. So you can see that we can make this a massively parallel infrastructure. So if we now look at it in terms of increasing computing power and with a number of cores, then you can see that something that took a long time actually could be cracked within hours, given improvements in computing and improvements in the number of cores that we can actually have. So this is an example of a GPU, and it's possible for a GPU to implement hash cracking, encryption cracking, and so on. And basically it has a number of CUDA cores. This one has 3,584 cores. So it will split the problem into those number of cores, and will probably create a speed up compared with a normal processor. There is also memory, local memory, to make it even faster, and obviously they'll get quite hot. So there is a heatsink and a fan on there too. So these are often used in arrays. So it's possible on the AWS cloud, for example, to buy an instance, a compute instance that has a number of GPUs integrated into it. So it doesn't have to be hardware, it can be done in the cloud too. Okay, we obviously see this within Bitcoin mining. So this is a Bitcoin mining factory, and we can see here these are racks and racks and racks of GPUs, and you can see we need a lot of electrical power to be able to run these, and they need to be cheap electric power, because obviously the benefit is that one of the GPUs discovers the hash that's required for Bitcoin, and then we'll get a reward. So to be able to support all of the electricity and the investment in GPUs, then obviously there's got to be an incentive that winning the Bitcoin hash competition will result in a profit. Okay, and we can also we'll use these with Ethereum mining, and there are pages on the internet that will actually show roughly what would be the payback, but obviously someone would have to keep their mining infrastructure online for this to maximize the income. Okay, so that's a basic introduction. Now let's look at the basics of symmetric key. Basically, with symmetric key, we have the same key, the same secret key to encrypt as we have to decrypt. We change from plain text into ciphertext and then into plain text again. And as long as Eve doesn't know what the secret or the symmetric key is, then Bob and Alice are secure, hopefully if they have a big enough key size. So we're obviously encrypting a lot of data. So the way that, or one way that we do it, is to split the data up, because it's quite difficult for a processor to be able to implement the encryption methods. The best way is to go small and to have very small little blocks of data that can be encrypted on their own. This allows for very simple hardware to be created, and all we really need is to operate on some bytes at a time, do that operation, and we can even make that be done in parallel if required. So what we have is what's called a block size, and the block size defines how we chop the data up into blocks, and then we will process each of these and cipher them. A typical block size is 128 bits or 16 bytes. Okay, so all that the method has to do is to take 16 bytes at a time and then do the encryption, and then on the other side do the same, take the 16 bytes that are being ciphered and then decrypt these into 16 again and build the data back up again. So these create a cipher block. We take our secret key or symmetric key, and we also add a little bit of salt to make sure that we change the cipher each time. This then goes into a block in there. Okay, so we take the plain text, we can chop it up, and then we can encrypt. So let's see if we can see this running in action. Okay, so we take the message QWERTY, and we've got a 16 byte 128 byte block, and we can actually see here is our data in there, and this part here is what's called padding, and I'll explain that in a little minute. So we can keep getting more, and we can keep filling up our block until the first block will become full, and we're nearly there. So we're up to 16, 15, and there we go. Okay, so you can see what happens is that when we go over the 16, then we now build a new block, and here's the first block, and then there's the second block in there. I'll explain, as I said, I'll explain the padding. Okay, so this is the this is an important element of our cipher, is that we fill the blocks, and then once we fill that block, we'll go on to another block until we get to the very last block. The other method that we have is what's called a stream cipher, and this is a much simpler cipher. What we need to do is be able to create our secret key, some salt, random, and then we create what's called a pseudo-infinite key stream. It can go on forever, but basically it fits exactly into the plain text size. So if the plain text has 10,000 bits, then the key stream has 1,000 bits. So we have some algorithm that runs that will be able to create an infinitely long key size, and we just create it for the size of the plain text. And then all we do is that we create with an XOR operation. If you remember, XOR is just like that. And the advantage with XOR is that if we XOR again with the same key stream, then we'll get our plain text back again. So it basically just goes into an XOR gate and we create our cipher stream. Very, very simple implementation. And ChaCha20 is one example of using that. And we should find that the length of our key stream, of our cipher text, will be the same length as our plain text. Remember, in blocks, we went in blocks of 16, but in this, we will the size of our cipher stream will be the same as our plain text. Okay, so we can encrypt that, and here's our cipher stream here, and we're decrypting it again. So as long as Bob and Alice have the same seed value and also salt value, then they will be able to encrypt and decrypt. So it's very important that the salt value goes along with the cipher stream, because if Alice doesn't receive the salt value, she won't be able to decrypt either with the block cipher or with the stream cipher. So we find when we store the ciphertext, we'll store the salt value with the ciphertext. So that's not a secret. Okay, so we can have various modes in our encryption, and the three main modes that we have are stream, block, and what's called AEAD. Okay, block we came across before. Block is CBC, we'll see that in a little minute, or cipher block chain. And stream cipher feedback block is one mode that we can have for our encryption. Here it's here, and that creates a stream cipher. And then we can have what's called authenticated encryption. The advantage with authenticated encryption is that we add in something extra to authenticate the data. So it could be a TCP port or a session ID into our encryption is added in, and Bob and Alice can actually use that so that Eve can't play back the cipher in another session. Okay, so those are the core modes that we have, and I can demonstrate some of these. GCM is one of the is an AEAD method, and we can add in some authentication data into that there. Okay, so we can try cipher feedback mode, and hopefully that will work okay. There we go. Okay, so there's the cipher stream, there's the salt, and we can see that we can decrypt here. And we can also try our stream cipher, and there it is there. So we should find that the stream cipher is quite useful because it only gives us the length, where if we go for our block cipher, then shouldn't change until we go up to the end of the block. So if I now try to fill the block, then you can see that the cipher is now more than one block there. Okay, so there's the three main modes, AEAD, block, and stream. Stream is much faster. GCM mode here is also a stream cipher, but it brings in the authentication into the data. Okay, so the most basic mode that we have is what's called ECB, or electronic code book. That should be book there. So with this, there is no, we just basically take each block and cipher it. So there is no salt added into this at all. Okay, so this is without any salt. A popular method for adding salt is to add in an XOR into the message block, and then to chain the output of one block into the next, and so on. So we end up chaining it. So we add the salt to the first, and then we chain all the way through. So this obviously has advantages, that the cipher will always change depending on the salt, even if we have the same message. And then for our AEAD, or authenticated encryption with additional data, we add an extra piece of data into the encryption process. This is a known piece of data, so there is no secret. It's not like the key, but and obviously the salt needs to go along with it. But this data is added in to the stream. So typical is that it's a session ID. So as long as Alice knows the session ID of the data that's being sent, then she'll be able to recover that and put that into the decryption process. But it can also be other things like the IP address of Bob, or any additional data that can be added to it. This will mean that for a different session, it's not possible for Eve to play back the data to Alice, because when she adds a different session ID, then the decryption process won't actually work. Okay, so what about padding when it comes to our block ciphers? Well, there's different methods that we can use, but the most popular is called CMS, and that's defined in a number of standards that were defined by RSA, the company RSA, many years ago. For this, we pad the same value for the spaces on the last block. So if there are 6 spaces left that aren't filled in the last block, then we'll fill it with the value of 6 times. If it's 5, it's 5 times. So here we go, and this is the word hello here, up to there. So HELLO, and this leaves, so that's 5. This leaves 11 spaces left in our block, so we fill it with the value of 11 in there. Okay, so we should be able to demonstrate that. If we just have a look at our padding again, go back to here. Okay, so if we have hello, then we can see we're padding with 0B or 11. If I now add another one, then it's there. And then if I keep adding, we can see the value. I've got 6 spaces left, 3 spaces left, 1 space left, and if I put one more character, then we go into another block, and then this time we're obviously padding again, and we can keep going, and so on. So that's padding with a value of 15 there. Okay, so the pad applies to the very last block, and we need to pad. Then we encrypt, we then decrypt, and then we unpad. So the padding needs to be the same on either side. Okay, so now let's look at some methods for symmetric key. So these are some of the typical ones: DES, 3DES, blowfish, 2fish, RC2, and so on. But NIST had a competition, and it was the Raindal method that was selected. That then became the standard as AES, and it's the most popular method around at the current time. Okay, there's also 3DES, which does DES 3 times. I'll show you that in a little minute. We can also have some of Ron's ciphers, RC2. And as I said, the AES Raindal is the most popular one. We can get 3 key sizes, 128, 192 and 256 bits. Okay, so we have this method, and obviously Alice knows the methods that are involved. So one problem that we have now is that Eve could obviously do a playback attack on the cipher. So she could copy and paste the ciphers together to create a perfectly valid method. So the way that we make sure that the encryption always changes is to use a salt value when we're doing our block encryption. Okay, so there's electronic code book. Basically, the same text will lead to the same ciphertext each time. If we add in what's called an initialization vector or salt value, and it's random, then we should be able to, and ever changing, we should be able to change the ciphers that we get even for the same value that we apply. Okay, and as I showed you before, we have an initialization vector and a key, and then we can feed the output of one block into the next, and so on. So here's an image, a well-known image, and if we use ECB, we can see that although we're encrypting, we can still see the penguin. And the reason for this is that similar areas are encrypted for the same data output. So you can see here that these areas are all the same with their pixels, the way that JPEG works. And so when we encrypt each of these blocks, they will come out as the same values in the encrypted image. But look here, when we add in salt and when we chain, we end up with what looks like noise. So this is what we would expect from an encrypted file, completely random values from there. Okay, so here's an example here. In this case, I'm using DES, which has a 64-bit block size. So this is 64-bit or 8 characters, and this is my data stream here. So let's try and encrypt it. So when I encrypt that block, then I get this, and obviously when I encrypt this block, I get this. So the encryption shows that we repeat, so there, and then we repeat again, and so on. So it could be possible for someone to be able to break this cipher because they can actually see patterns repeating of common cipher blocks. So ECB is not a secure method of encrypting our data. Yes, well, I won't go into great detail, but basically what happens is that we go through a number of rounds, and in each round we use a part of the key, and then we'll use the whole key in all of the rounds. For a 128-bit AES, we have 10 rounds, so we go through 10 rounds of this encryption process. basically what happens is that we do some scrambling and so on here, and then on the other side we just reverse what we've done. So everything we did here we reverse, everything we did here we reverse, and so on. So we go through and then we undo here. And if you don't know the key, it shouldn't be possible to be able to find out what the decryption process is. So in each round we use a bit of the key. We then use what's called a substitution box or an S box. With this we take a byte value. So a byte value might be 43 here. And then we feed it into the S box and it'll give us a value out. So 4 and 3 will give us 1E as hex. So this, the output of here, one of the values would be converted from 43 into 1A. We then normally we take the 16 values and we put them into a 4x4 array, and with this we shift the rows. So we take some rows and we shuffle them. So we shuffle the data here, and then we mix the columns. So we basically then take the columns and we shuffle the columns. Okay, so the first process is like shuffles like this, and then the second process shuffles like that. Okay, so the basic process, S box, row shuffle, column shuffle, and then we go through, add the key, and then we go through 10 rounds of that for 1 to 8, and that's it. Then on the other side we just do the reverse. So we do shift. If we shifted the columns, then we unshift the columns, and if we shifted the rows, we unshift the rows and go back, and then we'll go back to the S box and we'll do a reverse S box. So if we had the value of 1E here, so 1 and an E, and 1 and an E should give us our value back again. Just let me see. So 1E, we should go back to 43 again. Oh, sorry, it was 1A is our value, 1A. So if we go for 1 and then A, we get the value of 43 back again. So the S box is doing a scrambling for us, but when we do the S box on the other side, we do the reverse of it. Okay, so that's as much detail as we'll go into that, but just understand that we use a bit of the key, we go through these rounds, and then we just do the reverse on the other side. The S box is keeping us nice and secure with the scrambling. So here's a number of modes that we have from there. So we can see here that we have padding. We can see the cipher here, and there it is in base 64, and we can actually decrypt. So let's see. Okay, here's an example. This is ECB, this is CBC, this is CFB, which is a stream, OFB, and there's another mode that we can have called CTR. Okay, we'll just look at another method that's interesting, is 3DES. So the problem that we had with DES is that we only had a 56-bit encryption key. It was 64 bits, but 8 bits were used as parity, so it was only 56. So as we saw earlier, 56 bits is really easy to crack. So there was a dilemma: how could we make DES more secure? And the way that it was designed is that with 3DES we have 3 encryption processes, and we then use 2 parts of the key. So 56 and 56 is 128, So when we take the two key parts, that's the equivalent that we have. And then we use a standard DES encryption here with 56 bits with the first key. Then we decrypt with the second key and then re-encrypt with the third key. It might seem strange, but that works. It's obviously going to be slower than if we just did it in one. And the reason it's like this is if we now make K2, K1, then this and then this becomes null and void. And then all we have really is one round of DES, which gives us our DES. And this allowed us to have chips or software that allowed us to be able to support both DES and 3DES at the same time. So it's just an interesting little detour to show how the 3DES was actually created. But one of the most popular, not the most popular method as an alternative to AES, AES is still very much the most widely used method, is CHA-20. It's a very fast method, and we can use Poly 1305 in order to be able to create the authenticated ciphers than before. Another stream cipher that's quite popular, it's good for IoT and things like applications like that, is RC4. Okay, the standard was written by Google, and certainly Google see it as an excellent cipher, and many applications now use CHA-20, especially within Google Chrome and so on. Okay, so here's a little example here. I'm just going to use a stream cipher here for that, and hopefully that will work okay. And it's now integrated into TLS, so it's a standard part of the encryption that we can use for our TLS connections. Okay, so as I said, we XOR the key stream. We create an infinitely long key stream and XOR it with a data stream. So this is RC4, and we create the key here. So we create the infinitely long key by calling up this method here. This here creates our S box, so we can have an S box in there. But here is where we generate the key. And in Python, there's a yield k. And this looks as if it's in an infinite loop, but it isn't, because what happens is that it will yield. And basically what happens is that we have a block of data, and then every time we need a new part of the key, then Python will provide that. So that's what the yield k does. It stops that method, only returns back a part that we need for the key and the key stream, and then we can then just XOR it together with it. Okay, so let's look also at what's called key entropy. So key entropy defines if we have a large key space, 2 to the power of 128, and if we use a password to be able to generate the key, then we might be decimating the key space. So for example, if we only had 1024 passwords, then actually we only have an equivalent key size of 10 bits or so. So the key entropy measures the equivalent size of the key. Anything less than 72 bits would be seen as a weak key. Okay, so the way that we do it is that we take log to the base 2 of the number of phrases that we have. And log 2, you won't have a log 2 button on your calculator. You basically take log 10 and divide it by log 10 of 2. So if we have 1024, we take log 10 of 1024 and divide it by log 10 of 2. So we can just try that out just now. So let's get our little terminal, and we'll just open up Python, and then let's say that we have the number of passwords is equal to 5,400, and we want to work out the equivalent key size or the key entropy for that. So the entropy is equal to, let's import our math first, and so our entropy is equal to log to the base 10 of passwords divided by log to the base 10 of 2. Okay, so our key entropy is equal to 12.4. So you can see that's not a very strong range of passwords. It's only 12 bits, which is quite easy. So we can work out, if we use passwords, we can work out how many passwords that we've got. So let's say that we have numeric values. So that's a numeric value is between 0 and 9, and we have a PIN number. So let's say in this case we have eight numeric values as a PIN number. Then that's obviously going to be 10 to the power of 8. Okay, is the number of possible passwords that we could have with a 10 with 8 numeric digits. Okay, so we'll work out what the entropy is now, and we can see, we'll see that it's 26.6, so it's not very secure either. So now let's go for lowercase values. So it'll be 26 to the power of 8 is the number of passwords that we have. So let's work that out, and we now see that it's 37.6. Still not great, but it's improving all the time. So we can then go for upper and lower case. So that's 52 characters. 8 gives us this. And we can now see that we're now 45. So we've increased by about 7 bits there. So that's double, 7 times. So it's made it a lot more difficult to be able to crack this. And now if we go up to 62 characters, if we take additional characters such as tilde and hash and so on, then we'll see that that has improved up 2 more bits, but that's made it double, 4 times more difficult to actually do that. So we can see here that we really need to be using much bigger passwords than 8 characters. So let's go for 10 characters, and we'll try that out. So now for 10 characters, upper and lower case with additional characters, and then our entropy is nearing 60 bits, so it's much better. So probably we want to be going up to 11 bits to make sure that we're secure, to get our entropy up over 72 bits, hopefully, and that's certainly approaching that. So this is what's called a measure of entropy, and it's highly important when it comes to the security of the keys that we actually create. If they're random keys, then everything is okay, because it'll take the time that we saw earlier to be able to create that. Okay, so I'll just try lowercase. So for lowercase there, let's go for a cracking rate of 100 billion. And we'll just have 1 processing element, or we could have 16 if we wanted. Yeah, we'll just go for 1 just now. So for 8 character passwords, it takes 2 seconds to crack every single password there. If we now go up to upper and lower case, 8.9 minutes, nearly 9 minutes, will crack every password. That's upper and lower case numeric, and now with the extra characters. For 10 characters, 1.5 years to be able to do that. But if we had even better cracking, then we can see here that even 10 digits with upper and lower case and numeric values and extra characters still only takes 57 days to crack every single password. So we need to probably be up here with 11 digits and more to be able to cope with the possibility of our password being cracked. Okay, so that's key entropy, and we typically define that in terms of regular expression type syntax there. In our last topic, we'll look at how we can use our keys within a cloud-based infrastructure, because more and more we're moving to the public cloud to be able to do our encryption, our processing, our storage and so on. And it's highly important in the public cloud that we encrypt data, because we can't hide behind an on-premise firewall and so on and have access controls. We are now in the public infrastructure. So it's highly important that we encrypt data. So the three main formats that we have to represent our keys and our encrypted data, and we'll see this later on when we look in more detail at this, is the DER format. The DER format is what's called the binary format. So each of the hexadecimal values means something there, and then the program will be able to interpret that this is a key or a signature or something like that. We can also have what's called the PEM format, and this is a useful method because it has this header and footer, which actually defines if it's a key or a signature or something like that. And then we have base64 in between. This is a good format to be able to copy and paste into an email or a terminal and so on. And increasingly these days we have what's called a JSON format, and that uses key pairs to be able to just go for a plain text data blob. So in the lab we'll be looking at how we can do this in AWS. And with AWS we can have either Amazon managed keys, so Amazon has their own keys that they use across many instances of data storage. So this is elastic block storage, which is just like a disk that you add onto your server or into S3 buckets. That's where we store data objects. So if we want, we can use Amazon standard encryption keys to be able to encrypt the data into there. If we don't trust that, we can use our own key management system. And the KMS, AWS KMS, allows you to apply symmetric key, HMAC, public key encryption, and digital signatures. It will also store our public keys so that we can distribute them. But the KMS links to a hardware security module, or HSM. This is the place that we store our secret keys, our private keys and public key, and also our symmetric keys. So this is stored in a place which is called FIPS 142 compliant. It has been audited so that it's not possible to get access, even Amazon, to be able to get access to that chip and to be able to look at the keys that are in there. Okay, so when we use this, the keys are actually stored in this HSM, and we can expose the more public elements that we have within our KMS. Okay, so this is us creating our keys here. I'll show you that in a little minute. We can either have managed keys or customer managed keys. In this case, we'll use custom managed keys. When we create our keys, we can either use symmetric key or public key encryption, symmetric key or asymmetric key. And then we can use symmetric key, and explain this later on in another unit, to either encrypt and decrypt. That's what we covered today. Or we could use it as an HMAC signature, and I'll explain that later. And this gives us a basic example here of the encryption process using the AWS command line. So let's actually see if we can get an example of this. Okay, so I'll just start my lab here. Let's take a little minute. So we can either use the SDK with Python, we can use the CLI with a command line, or we can use the management console. So in this case, we'll start with creating the keys in the command and the management console, and then we'll be able to use them in the command line console, the CLI. And hopefully in the lab we'll be able to also use Python to be able to implement these using the SDK. Okay, so that's it started. Okay, so then we'll go to our KMS, so that's good, it's already there. This is my KMS store. So I can either have I can either have the standard keys that are used. RDS, if you're interested, is the database. So Amazon can manage the encryption keys for my RDS database, such as MySQL, or I can create my own keys here. So let's create a key. So we'll go for Symmetric, and we'll go for encrypt and decrypt, and that's the only option I need there. I call it my key 2, and just give it a little description, and I can tag it. So if it's used ever in any operation, I can put a special tag on it, so that if somebody uses this key, I can trace what they've been doing with it. We then define a number of rows. So you give the minimum rows required to be able to look after the key, and then you define how the key can actually be used in there. So we'll just take the defaults for that. So this gives us the basic setup for the key and how it can actually be used. Okay, so there's my key there. At any time I can disable my key, but watch that you don't delete the key from there, and I'll confirm that I just want to disable it, so I don't get charged for the key. If I keep the key alive, then obviously I get charged each month for creating this key. So sometimes you can disable from here. Okay, so there is our basic setup that we have. This is symmetric key used for encryption and decryption. No tags. We can apply key rotation, so that every single year, say, it will change. Obviously Amazon need to remember all of the keys, because if something was encrypted with something before our new key, then we need to be able to decrypt it. So Amazon will look after all those keys to make sure that they can still be actually used there. This is our identifier, and then we also have an alias, so we don't have to use the full Amazon resource identifier, we can just use the alias in here. Okay, so that's our key created from there. What we can then do is we can go and use that key. Just show example here. So this is my example here that I've just created. We can go ahead and we can create our file. Here, just let me get my console back again, my CLI. There we go, so I've got my CI, so let me just create a folder, just call it my key, and I'll create a file here, and I'll just put some text in there, and I'll quit. Okay, so then let's do that. So I'm going to use the CLI to be able to encrypt. So just let me see that I have a key that's called that. My key sim is here. I've created that already. It's a symmetric key, so everything should be fine there. So just let me see, that's my alias. I'm going to take my text file called one.txt, make it into a cipher blob, and then I'm going to output it here. Oops. I just need to get my key right. My key sim, my key, it's run the wrong way. So just let me get my alias right and we should be good to go. So it should be called my key sim. Good. Okay, so that's what our cipher looks like. I've outputted that in a text format so that we can actually see it, but normally it would be in a binary format that we have. Okay, so we can then we now need to put this into a binary format. So here's we can use this base64 command to do that. So this is the binary format now of our ciphertext, because we need that now to be able to decrypt it. Okay, so that's what it kind of looks like. Now we're going to decrypt. So we'll take our AWS command with the key, hopefully, and we'll just paste that into there. And obviously I need to make sure I'm using the same key. So just let me get that key right, and I think it was called my key sim. Just let me see where I went wrong there. So, oh, I've got too many characters in there. So let me get that there. My key sim. My key sim. Just let me check that that's the key that we've used. We're taking our encrypted. Just let me see. We've created that, and then we'll do that. All right. Just got a little unknown option for text. Just let me see where I went wrong there. Unknown option in text. All right, got an extra little word in there. Just let me remove that. Okay, and then we'll just see what that looks like. So that's in a base64 format. We now need to be able to decrypt that. So we use the base64 format, the program, to be able to decrypt that. The -I takes the base64, and we're going to decode that. And you can see that this works. So I just need to make sure that that text part is changed there. Okay, and then we can implement this with Python. So here's a little Python code that you can try in the lab, but we use the Boto3 integration, and it basically just does the same steps as we created there. Okay, so make sure you try out both the CLI and the Python integration in the lab. Okay, so that was that integration there, where we used the key, used the alias, and we were able to encrypt and then decrypt with that. But we're also able to do that with Python or whatever programming language that we want. Okay, so that's been an introduction to symmetric key encryption. Thank you.